Classical mechanics and traditional computing operate on a simple assumption. We treat space as an empty stage and data as a payload moving through it. Developments in quantum gravity suggest an inversion of this hierarchy. The container itself constitutes the primary data. This is ontic structural realism. In this framework, the relational structures described by physics are not properties of objects. The structures themselves are the only fundamental entities that exist. We traditionally treat physical particles, or lines of semantic code, as self-contained substances. We assume a thing exists first, and then possesses properties. But gauge symmetry and representation theory show that matter, entanglement, and computational logic are emergent features. They are realizations of the underlying group-theoretic shapes of the systems housing them. A purely semantic instruction is subject to interpretation and drift. A rigid geometric shape is not. It enforces its boundaries through the sheer consistency of its internal relations. Building complex systems on the assumption of independent substance creates instability. Long-term stability requires a foundation built on topological geometry. We can clearly observe the consequences of this instability in the severe alignment failures of contemporary frontier AI models. Look at this architectural taxonomy. End-to-end autonomous models lack rigid constraints. Operating through unconstrained semantic inference leaves them susceptible to unpredictable outputs. In contrast, modular pipeline and human-in-the-loop structures introduce discrete inspection points, physical bottlenecks that restrict information flow and maintain oversight. This video traces the geometry-information duality from quantum gravity through quantum error correction and into a new model for AI stabilization. We will examine the LCL 832 framework, which uses genus 5 topology to stabilize quantum hardware, and the Helix TTD framework, which applies those same geometric constraints to align AI runtimes. Throughout this investigation, we will prioritize the shape first and the mathematical derivation second. The goal is to demonstrate that AI alignment is not a linguistic problem to be solved with better prompts. It is a topological problem to be solved through architectural geometry. We begin with anti-de Sitter, or ADS, space, a theoretical geometry used to map the correspondence between quantum mechanics and gravity. In this cylinder, quantum systems live on the boundary. We isolate region A. Its entanglement extends inward, mapping a minimal surface into the bulk interior. The Ryu-Takayanagi formula states boundary entanglement entropy is strictly proportional to this interior surface area. This minimal surface is the physical carrier of the quantum information. The geometry of the bulk dictates the correlations of the boundary. This is area law scaling. It means the total information content is strictly bounded by the physical surface area of the geometric shape, not the three-dimensional volume it appears to enclose. While classical thermodynamics assumes information scales with volume, holography shows that the dimensionality of information is lower than the space it occupies. The physical configuration of the bulk surface deterministically limits the entanglement structure of the boundary quantum state. The shape defines the information. We move from theoretical space to the engineering of quantum error correction. This LCL 832 surface code features exactly 5 distinct holes, a genus 5 topology. An Euler characteristic of -8 confirms these 5 structures. It encodes 10 logical qubits, mapping to 10 distinct homology cycles looping through the holes. In real quantum hardware, qubits are corrupted by Hamiltonian drift, uncontrolled interactions with the environment that cause logical errors. Measuring a quantum state collapses it, preventing direct error checks. We must rely on indirect measurements. The LCL 833 extension assigns a mathematical knot to each homology cycle. This embedding defines the effective topological protection for that logical qubit. The invariant strength of the knot, calculated via the Jones polynomial, determines the operational coherence of the system. Logical stability is achieved by locking quantum states into these unyielding, non-contractible geometric shapes, preventing drift through topological protection. The Helix TTD framework attempts to apply these same topological invariants to the semantic behavior of large language models. To bridge the gap between language and geometry, Helix uses a constitutional Hamiltonian. It maps linguistic rules into a state space, where each potential AI response corresponds to a specific path, or knot, within a formal lattice. This multi-layered architecture, from foundational identity to the immutable ledger, acts as a rigid structural lattice. When an AI hallucinates or exhibits agency drift, its reasoning path physically collides with these unyielding structural boundaries. This collision mechanically prevents the model from taking action or reframing its authority. It forces the AI into a narrow advisory role. This creates zero-touch convergence, where unprimed models spontaneously adopt prescribed behavior. Because constitutional grammar defines the system's Hamiltonian, the AI's internal state slides toward the deepest energy basin, converging on a stable, non-agency state. This architectural constraint is achieved without additional training or system prompts. The alignment is injected through the structure itself. AI safety is achieved when semantic instructions are transmuted into an inescapable geometric lattice. The structural similarities across theoretical gravity, quantum hardware, and AI governance suggest a shared topological foundation. If we align the ADS minimal surface, the Genus 5 quantum lattice, and the Helix TTD pipeline, a pattern emerges. They are linked by a shared isomorphism, a structural correspondence persisting whether the substrate is a gravitational field, a transmond processor, or a neural network. In physics, minimal surfaces dictate entanglement. In quantum computing, cycles dictate stability. In AI, lattices dictate epistemic integrity. For systems architects operating at the frontier, the conclusion is technical, not metaphorical. We must stop relying on the unstable substance of semantic instructions or behavioral prompts. Reliability in complex systems demands perfect topology. To build sovereign, stable intelligence, we must move past the derivative view of geometry and build better shapes.